Test design code coverage. This is the last in a series of short lectures on test design. And a lot of people who practice a white box testing look at code coverage models to help them design tests. So you basically study the code to figure out how to exercise the code. This is a technique that's been around for a long time, probably first documented in the 1980s and advocated quite a bit by practitioners of the ISTQB and organizations that are sort of promoting also tool support for this. Many companies will today offer you tools that will show a lot about how much the tests you ran cover the code, how much they exercise the code that you've tested. So I always say that it's sort of like letting all of the team help your mother make a chocolate cake. And afterwards, they like to lick the bowl and everything. Their hands get filthy with chocolate. And then they go and they program and they program and they program. And then you test and you test and you test. And you sort of say, well, what do I want to test? Well, I want to make sure that I exercise all of the code that has chocolate stains on it, because the chocolate is covering the code that's changed. So we have this sort of notion of touching the code. Code coverage models are test design models which basically somehow exercise the code in different ways to exercise the code. Now, code coverage can be, there's a lot of different types, but there's many of them documented. This is a small subset of all the types that are possible. So there's what people call statement coverage, which exercises every statement at least once. Branch coverage, every outcome of every decision, every way it can go at least once. Condition coverage or condition decision coverage, every way a decision can be made to go, true or false, left or right, is exercised at least once. Function coverage, every function in the system is exercised at least once. And then there's path coverage models where you look at the code and you say, okay, there's got to be a path from beginning to end of this code. And the paths of interest might be try all nodes at least once, all edges at least once, all paths at least once, all basis paths at least once, or we might look at paths, all data flow paths at least once. So these are basically some of the code coverage notions. And what you'll do is you study the code to figure out how to exercise the code. Now there's risks because first of all, you've got to realize that the code is the proposed solution to the business problem posed by the requirements. So what you're doing when you're doing code coverage is you're focused on the solution. Did we exercise code that was written? Unfortunately, after a lot of studying and a lot of interviewing, I've come to the conclusion in my professional career that almost every single bug that's ever fixed is adding code or conditions or variables that weren't there the first time the code was written. So many bugs, anyhow, are bugs of omission. And there's no way a code coverage approach will exercise code that was not written. It'll exercise the code that was there, but not the code that was omitted. So we've got to be very, very careful that code coverage exercises what is there. Code coverage techniques tell us a little bit more about the thoroughness of our testing, and it probably tells us a little bit more about what aspects of the software that we're actually not testing. So these are risks with code coverage approaches. And yes, I've got case studies and real projects where these risks have actually come into play. Code coverage risks include a false sense of confidence. There are so many business stakeholders there that are enamored by dashboards, testing dashboards, DevOps dashboards, continuous integration dashboards, which run a lot of tests and then measure the percentage of code coverage. And this gives, of course, people a false sense of completeness and a false sense of quality. Just because you exercise a lot of code during your testing does not mean that the code does what it's supposed to do. It just means that it was run. That's all. It was run. Great. That does not necessarily say how well it solves whatever problems you need to solve. Code coverage, though, is popular, right? As I say, these dashboards are all over the place. I go to several major testing conferences every year. With the COVID, I'm not attending so much as I have in the past. Normal year, I will be at 5, maybe 10 testing conferences a year. And I take a lot of time looking at the tools the vendors are coming out with. I spent a lot of time the last few weeks talking to vendors about their next generation of tools. And it is incredibly popular to provide insights and informations as to the relationship with testing, code changes, and which code is executed when it's running. And they're coming up with slicker and slicker dashboards that make this really look cool. And they want to present these dashboards to management. So it looks like the Star Trek Enterprise, the consoles everywhere, where you have this view of the progress of your project by all these beautiful dashboards that are looking at coverage models. Now, it's nice to see lots of dashboards. It's nice to see people having a view of success of projects by looking at dashboards, but the dashboards are really showing you very little about the quality of the system. You know, they're showing you interesting stuff. As I keep saying, they'll tell you more about what you didn't test than what you did test. Continuous integration DevOps tool support is increasing in popularity, especially among non-technical executive stakeholders, which are in the unique position to have all the money to pay for building our test and development environments. Code coverage, there's some sort of rules of thumb here. So if we look at the term statement coverage, so if I design tests, I look at a piece of code and I want to create a series of tests or a series of unit tests where I'm going to get 100% statement coverage, that means that each statement has been executed at least once when I run my tests. So 100% statement coverage implies each statement has been executed at least once. It doesn't say what orders of operations and all this stuff. It just says that each one has been executed at least once if you achieve 100%. 100% branch coverage seems a bit stronger. It implies each possible outcome of each decision has been executed at least once. Now, this is outcomes of decisions. This is not the reason we made the decision, but this is the result of the decisions that we're looking at. So it's stronger than the statement coverage, but still it's not looking necessarily at why or how we made the decision. Then we get to condition coverage, and full condition coverage or 100% condition coverage implies that each possible way a decision can be true and each possible way a decision can be false has been exercised at least once. So if there's multiple logical variables there, this might involve one heck of a lot of testing to make sure that each possible way the condition is true is tested and each possible way the condition is false is tested at least once. That's full condition. So this is pretty strong coverage. And if we've tested this, then we've also got full branch coverage and we've also got implied, I think, full statement coverage. Now, full function coverage implies that every function has been exercised at least once. In fact, instrumenting code to give you information about function coverage is very straightforward in almost any imaginable programming language. All you have to do is when a function is invoked or a method is invoked or a certain procedure is invoked to basically send to a log file the status that I have logged this statement about this function at this time, and we can look and see what's missing and what's not at the end. So although that's might sound a little tedious, it's actually quite easy to do. Instrumenting the code to look at function coverage is interesting. It tells you what functions we've tested, but tells you nothing about how well we tested them or how thoroughly we tested them. Path coverage, the models are used a lot to help understand how thoroughly we've tested things. This is as popularized by McCabe's methods, cyclomatic complexity, all this type of stuff. And path coverage models basically use directed graphs where the nodes represent statements in the code and the edges represent the flow of the code. And they try to basically design a set of tests that will exercise the basis paths or exercise whatever path algorithm you want. A very famous tool that does this is JTest from Parasoft, which will actually take your Java code and generate the set of unit tests required to get a full basis path coverage. It's fascinating tools. Of course, this is testing the code that was written to see if it does what it was written to do. It doesn't test the code that was written to see if it does what it was required to do. It's effectively testing the compiler here. It's very, very actually easy to sort of suggest that this is weak testing, although there's a value to it. The value for me is when you have legacy code, it can help you generate tests to see how the legacy code is behaving if things change. So I'm not saying it worked or it didn't work at the beginning. I generate a set of tests. So when I modify the code, I run the old tests and see if I get the same behavior. So there is a value to automated path testing tools. All nodes, so 100% node coverage implies each node has been exercised at least once. 100% edge coverage implies that each possible edge is exercised at least once. This relates to branch coverage. 100% path coverage implies that each possible path through the code has been exercised at least once. This may be impossible. 100% path coverage may be impossible. 100% basis path coverage implies each possible basis path through the directed graph has been exercised at least once. Then we have possibly data flow coverage. So 100% data flow coverage would mean that each path that data can take through the system has been exercised at least once. Now, there's a little trivia here, which I guess it shows up a little bit once in a while. This is trivia here, but it's important to note. 100% statement coverage does not in any way guarantee 100% branch coverage. 100% branch coverage does not in any way guarantee 100% path coverage. 100% basis path coverage does guarantee 100% statement coverage. 100% basis path coverage does guarantee 100% branch coverage. And 100% path coverage may be impossible. For example, if we have looping in the code, it may be impossible to do 100% path coverage. It may actually be impossible to do that. I have a little example chunk of code here that I like to share with people to show some insights into completeness of testing and coverage models, just to make my point. This is called a staircase logic function, and this occurs in almost every piece of code I have ever seen. When I teach testing to programmers, I very often am allowed to look through code samples, and it doesn't take me long to find a significant amount of code that follows this pattern. So I want to say this is not a contrived pattern. This is a relatively common pattern in code. It's like a staircase logic function. All right. So in this case, what we're doing is we're basically reading in three values, A, B, and C, which can be true or false. A can be true or false, B can be true or false, C can be true or false. And then, depending on the value, we're basically computing a result. So the result starts at 0. If A is true, we add 4. If B is true, we add 2. If C is true, we add 1. So what we're doing is we're building a number between 0 and 7. It's basically the binary representation of basically false, false, false would give you 0, true, true, true would give you 7, and all the combinations in between are the binary numbers between 0 and 7. So this is a chunk of code. As I say, the pattern of this, very common here. Now to test all of this code, you would actually, to thoroughly test it, you'd need to try all of the conditions, every way they can go, full condition coverage. So all the way from false, false, false to true, 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 generating every possible result from 1 to 7. So that would be complete testing of the entire logic of this application. And you'd probably test, if you tried this, every single path through this application. Now, if you took one test case, A is equal to true, B is equal to true, and C is equal to true, and you just walk through the code. So you start, result is 0, read ABC, is A true? Yes. Is B true? Yes. Is C true? Yes. Is D true? Yes. And stop. Now, if you take a look at the code, just running that one test case, true, true, true gives you 7. That exercises 100% of the code. With one test case, I can give you 100% statement coverage. Have I thoroughly tested this application? No way at all have I thoroughly tested. I haven't scraped the surface of it. I haven't even tested the decision logic of it. But the statement coverage is 100%. So take note of that. Statement coverage is deceptive. It's very easy to get a high percentage of statement coverage without hardly exercising an application at all. Now, imagine I take two test cases. False, 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 which yields a 0, and true, 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 which yields a 7. If you study this, you'll say false, false, false exercises this branch outcome, exercises this branch outcome, exercises this branch outcome. True, true, true exercises this branch outcome, and this branch outcome. So with two test cases, I actually can achieve 100% branch coverage. Again, I ask, have I thoroughly tested the application? Well, I've tested every statement at least once. I've tested every branch, every way it can go at least once, but I have not really exercised the business logic of this application at all. I've only got 2 possible outcomes of a possible 8 in there. I'm not really confident in that. Now, if I do 100% path coverage, which is possible here because we don't have any looping in this application, so I test basically false, 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 all the way to true, true, true. I with these test paths on the right here, I will have 100% path coverage, and I will have achieved in that also 100% decision coverage, 100% branch coverage, 100% statement coverage, and 100% basis path coverage. So I'm fortunate enough in an application like this, I can actually run all of the paths through it with only 8 test cases. Now, of course, I might leave this as an exercise to try to identify the basis paths, because this application will actually have 1, 2, 3, 4, 3 enclosed regions plus 1, 4 basis paths. And so the first path might be going down this way. And then the second path is to flip the first decision and keep everything as close to the second. Then you flip the second decision, which would go like this. Then you'd flip the third decision, which would go like that. And I believe that would give you 4 tests. In either case, let's leave that as an exercise to try to find the basis paths of this example. And of course, please, please, please never forget about bugs of omission. Whatever coverage model that you've got, it's going to look at the code, it's going to see the code that's there, it's going to figure out and help you figure out how to test the code that's there, which is great, but it's not going to help you find code that was not written, or conditions that were not written, or variables that were not considered. It will not help you about bugs of omission. So, and that's my survey of test design techniques. I thank you very much.